Did we get the number 4 and the number 1? Or did you come up with 1 and 1/4? 1/4 and 1? Oh, did I have it backwards? Did we do it backwards? We said x1 is alpha. x2, oh, I'm sorry guys, my fault. We were doing it in our heads. 1/4, right? Or you got 1/4, 1, either way, times alpha, right? And it's up to you whether you want the alpha. The eigenvector is a single vector. If you want all the possible eigenvectors for this eigenvalue, then you have a scalar multiple. But usually just one's good enough. Similar to mom and dad as homogeneous solutions to your second order differential equation. Right? If I just say e to the t is the homogeneous solution, c1 times e to the t is also a solution. Any scalar multiple. So how are you pulling that into eigenvectors? Okay, that's the big punchline. I'd like to get there, but there's a couple more things I want to make sure we understand about the properties of eigenvalues and eigenvectors. Go to the back, please. Before we start reading this, let's recap. First of all, I have a matrix. With each matrix, there are associated eigenvalues. For each eigenvalue, there is an associated eigen what?
Matrix.
Vector. Each eigenvalue has an eigenvector. Each eigenvalue and eigenvector are embedded in a matrix, not a matrix equation, just a matrix. If I give you a random matrix, there's a lot of properties you can pull out of it. If I just said, hey, let's take a look at this matrix, 3, -1, 4, 2, what can you tell me about it? Oh, it's got an eigenvalue of 2 with an eigenvector of 1, 1. Oh, it's got an eigenvalue of -1, eigenvector of 1, 4. We're describing the horses and cows. This is the horse or cow, the matrix itself, not the equation. This isn't to solve the diffie or to solve an equation. This just tells us something about the matrix. This says that if you use an eigenvalue of 2 and you use the vector 1, 1, this matrix times that eigenvector will be 2 times that eigenvector. Ax equals lambda x. Questions? Okay, let's just read through this. First of all, normalizing eigenvectors can be done. We all know what it means to normalize a vector, right? Instead of this vector, 1, 4, what should I do? What would be a normalized eigenvector? What is the length of this vector? Radical 17, agreed? So we really would have 1 over radical 17, 4 over radical 17. That's my normalized eigenvector. Just helpful. We can also, so we normalize them so that it has length 1 if we want. That'll be helpful for the fundamental solution set, or the fundamental solutions as we get to them. Each eigenvalue comes with an eigenvector associated with the matrix. If the eigenvalues are complex conjugates, you're going to have to do some complex numbers in your matrices. But don't worry, it'll come out clean. However, if your eigenvalue is complex, your eigenvector may be complex. You might get your eigenvector to be 1, 5 plus I. Or maybe 1 minus 3i and 5 plus I. That might be your eigenvector associated with an eigenvalue of 3i. Something like that. That's okay. That's fine. Make sure you can do that calculation, though, and work with them. That's what some of the homework's on. If they're complex conjugates, you might see a relationship when you do ax minus lambda x. If they're repeated roots, this is difficult. Look at the last star I wrote for you. Eigenvalues lambda with multiplicity. So if lambda came out to be 2, came out to be 2 again. A repeated root. We all know what I'm talking about? A repeated root to my eigenvalue equation. Are we all okay with that? If I had multiplicity, we'd have multiple eigenvectors that would be associated with that eigenvalue. That eigenvalue might have a couple eigenvectors. We might need an alpha and a beta. Multiple eigenvectors. Those eigenvectors together create an eigenspace for that given eigenvalue. Please ask questions. I'll say it again a little slower. If you have multiplicity, a repeated root to your polynomial equation with lambda, or your eigenvalues, if your eigenvalue is repeated, such as 2, if you had the eigenvalue of 2 show up 3 times, we had a 4 by 4 matrix, okay? I had eigenvalue of 2 repeated 3 times. Each one will give you a different, and by different I mean linearly independent eigenvector. Those together make an eigenspace, so that any vector in the eigenspace can be associated with that eigenvalue. One more time. If the repeated root happens, lambda equals 2, lambda equals 2, lambda equals 2, I will have 3 linearly independent eigenvectors, which when I put them together create a space, a 3-dimensional eigenspace. Any vector in that 3-dimensional eigenspace will solve ax equals lambda x for the eigenvalue of 2. Those are going to be complicated situations. We will touch on that briefly in this course, because we will not be doing much bigger than a 3 or a 4 by 4 system of diffie-qs. Okay. In other courses in linear algebra, it does take a much stronger hold, especially for those of you interested in statistics and economics when you have large data sets. And you've got to look for eigenvalues and a huge set of information. Okay, finally, make sure you read page 381 up to 382 this weekend on your own. Make sure you're comfortable with that. Any questions there? Okay, just real quick. Don't have to write anything down. Just pay attention because we're going to be doing this next week. Suppose I have my classic matrix P. So I have x prime, what we were working with diffie-qs now. X prime of t equals P times some constant matrix, let's say times x of t. X prime equals px. Or basically, what if I had x prime equals lambda x, some constant times the function? How is the derivative in this lambda involved? Oh, well, what's usually the solution if this was normal? X equals 5x. X prime equals 5x. How do I solve that diffie-q? X equals e to the 5t, agreed? Here, x will equal e to the lambda t. This matrix will be an e. How do we put those together? If only there were certain values lambda where when I took derivatives it would be equal to the vector. That's exactly the eigenvalues. You're going to see the eigenvalues come directly into play for diffie-qs. But we needed to spend this past 2 giant weeks on basic linear algebra to build up to